Okay, let's get started. Quick announcement before lecture begins. So reminder, next week is the midterm, right? Everyone knows this. Everyone has the date marked on their calendar. Check the website, know the correct time. Do not show up 2 hours early or 2 hours late or the day before or the day after. Show up exactly on time. If you have accommodations for the midterm, you should have received emails from us. If you have not, check the Piazza post on the date for when you should have received emails by. If you have not, please contact us. We're going to do everything we can to make sure that the exam will be have all the accommodations that everyone would need to have their best performance. There's a review session Monday night. The time is on the Piazza, the Ed post. I'm sure you've checked it. Everyone knows this. You've marked your calendars. Great. Tuesday, the day before the midterm, we will have lecture, but I'm not going to introduce some new concept that is not in scope for the midterm. So we will be basically doing new topics, but things that are kind of a review. So basically, like, we'll talk about, for example, principal components regression, which is just another way to review our concepts of the SVD and things like that, right? So yes, there'll be new stuff, but it will also be stuff that's, using concepts that are going to be useful for you on the midterm. So it's not technically in scope, but I'm not going to start teaching you about, say, duality or LPs on the day before the midterm, right? You'll all check out. So do come to lecture, and I will try to make it worth your while in terms of being here. Good. If you have questions about logistics, about the midterm, please come talk to me in office hours, or write to the class email, make a Ed post, and we will do our best to resolve this. Great. Okay, so that's that. I'm going to keep the screen up because I want to do a little demo halfway through the class, and we're not supposed to raise and lower the screen. So the screen will stay up, but it'll go up after the demo is done. Okay. So last time we introduced convexity of functions, and we talked about the first order conditions, right, for convexity. Everyone remember this? Yes? No? Kind of? Everyone with me? Okay. So today we're going to introduce the second order condition. And we're going to introduce the notion of strict and strong convexity. And this will all lead into the gradient descent algorithm. Okay? So the first order condition has to do with the first derivative of the function, right? If you remember the first order condition, what we wrote down last time was that basically, you need to have that the domain of f is convex. And for every x, y belonging to the domain, you want to have f of y strictly greater than or equal to f of x plus f of x gradient of f of x transpose times y minus x. And this comes basically from the Taylor expansion, right? So if you take the first order Taylor expansion of this function about some point x, right? You want to say that this first order, the linear approximation by Taylor series is below the function, right? So the tangent is below the line, is below the function. Everyone have this visual picture? Okay. the second order, and it's called first order because of this. So because it's dealing with the first derivative, right? And of course, you can only write this first order condition for a differentiable function. So it's possible entirely for a function to be convex, but not to satisfy the first order condition at every point because the derivative might not be defined, right? So it's possible for a function to be convex. For example, the absolute value function, which clearly is not differentiable at this point, but it will satisfy the 0th order definition of convexity, which is the Jensen's inequality definition of convexity that we talked about. But it won't satisfy this because, for example, a derivative is not defined at this point. Okay? Everyone see that? Question? Oh, no, okay, sorry. Yeah? Yes?
How can we apply this for a strictly convex?
We haven't even defined a strictly convex function yet, so wait. Other questions? Okay, good. So now from here we want to move to the second order condition. And here the second order condition is basically talking about the Hessian. And we want to have the Hessian be greater than or equal to 0. And what do I mean by this? So here, first of all, I should always say that I want to always have the domain of f be convex. And we need to have twice differentiable function. Okay? So when I say that this is my second order condition, I'm calling it second order because this is talking about the second derivative, right? The Hessian. So what is the shape of this Hessian in general? What kind of object is this? It's a matrix, right? So what do I mean for a matrix to be greater than or equal to 0? I'm writing this here. I'm not writing this as this. I'm writing it in this funny way with this curviness, and that's not just because my handwriting is bad, but I'm actually trying to write this curviness, which is a different symbol from the greater than or equal to. And when we write matrices greater than or equal to 0, this is the notation that we will use. And what this simply means is that the matrix is positive semi-definite, which we have already defined. And if I was to remove this equality sign here, and if I had the Hessian strictly greater than 0, that would mean I'm talking about positive definite instead of positive semi-definite. Okay? So this is just another notation for that. So this is, for example, the second order condition. And so, for example, you know, the standard example that one might give if you had f of x is equal to, let's say, x transpose qx plus, let's say, b transpose x, then the Hessian of this would be given by what? What is the Hessian of this f? 2q. And so basically, what do I need to look for to make sure that this thing is, actually it's not 2q. It's only if q is symmetric. For a general q, q plus q transpose, right? So to be able to check whether this is positive to be able to check whether this is convex, I want to check whether q plus q transpose is positive semi-definite. Everyone sees that? Okay, great. Which now brings me to the question that was asked, which is, what is this notion of strict convexity and strong convexity? So strict and strong convexity are two kind of gradations or layerings on top of convexity. And what I can say in general is that strong convexity is the strongest kind of convexity. So strong convexity will imply strict convexity. We haven't defined any of this yet. Will imply convexity in general. Okay? So something can be convex but not strictly convex. It can be strictly convex but not strongly convex. But if you're strongly convex, then you're also strictly convex, and you're also convex. Okay? Everyone sees that? Okay, so let's define strict convexity. So again, in general, I'm not going to write this out every time, but whenever I'm defining convexity, I always want the domain of the function to be convex. And then the 0th order condition is that for every x comma y in the domain, and in general, even if I don't write it out, I'm just always thinking I'm at f from, say, some Rn into R. I basically want Jensen's inequality to hold, but I want it to hold strictly. So I want f of theta x plus 1 minus theta times y to be strictly less than theta f of x plus 1 minus theta f of y. And when we defined convexity, if you recall, we had a greater than or less than or equal to here. But now I'm writing the strict inequality. Okay? This is basically the 0th order condition. Similarly, for a differentiable function, I could write a first order condition, which would be that f of y for every x comma y, it's the same thing, except what am I going to want here? A strict inequality, right? This is the first order condition. And the second order condition, similarly, is that you want your Hessian to be positive definite. Okay, question. Is your question covered already, or?
Oh yeah, it was covered.
Okay, good. Yes?
So is theta between 0 and 1?
Theta is always between 0 and 1. Yes, I did not.
Because if it equals 1 or 0, then we have like f of x is less than f of x.
Ah, yes, correct. You will not want to allow the equalities here. Good point. Thank you. Other questions? We're good here? So basically, what we're thinking about is, what is an example of a function that is, not going to be strictly convex? So for example, if I have f of x is this line. Is this a convex function? Yes. Is it a concave function? Yes, it is convex and concave. Is it strictly convex? No. What is the second derivative of this thing? 0, right? So it's definitely not strictly greater than 0. Okay? So this is, for example, one simple example of a function that is convex, but not strictly convex. Okay? And there's some more examples on your homework for exploring these. So take a look at that. Okay, can I move on? Other questions? Okay, I'll keep this down here so that people can take notes. Question while I'm erasing the board?
Does that mean it's convex and concave, or neither convex?
It is both convex and concave. Yeah. Yes, question in the back.
Any function that kind of has like a bowl structure strongly convex?
We will come to strong convexity. We have not defined strong convexity yet, but we will see exactly. Function.
Not strong, strictly
Essentially, if you wanted, yes, but you had to verify the conditions, right? So you might have like piecewise, you might have non-linearities in there that you might have some flat parts that you want to check out, right? Simeon, question?
Yeah, I was just saying, so for strict convexity, it's always less than.
For strict convexity, the zeroth order is a strict less than, yeah. That is correct. Finally, strong convexity. So again, here I want to think of f that is differentiable. And I want to think of the domain of f is convex. Then I'm going to call f is mu strongly convex if for every, let me write it, maybe I should write it, if, no, if for every x, y in the domain, I have that f of y is greater than or equal to f of x plus gradient of f of x is x plus mu over 2 y minus x squared. X not equal to y. Okay? I've written this equation out. Now let's parse it together. So in contrast to strict convexity, when we talk about strong convexity, we're talking about also a degree of strong convexity. So there was no mu strict convex, like nothing like that in strict convexity, right? It's either strictly convex or not. But with strong convexity, there is this parameter mu, which captures a degree of strong convexity. How strongly convex are you, in a sense? Okay? And here, what we're trying to say with this, what is this? So this is f of y. This is the function value at some point f of y. What am I going to say about what kind of expression is this? This is a polynomial, okay? And what kind of polynomial is this? It's a quadratic equation, right? So if I was to write out the second order Taylor expansion, right? The Taylor expansion, what does it tell me? That f of y, I say, is approximately equal to f of x plus f of x, y minus x, plus 1/2 y minus x transpose Hessian y minus x plus dot, 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 right? This is the second order expansion of a Taylor series, okay? So the first order condition, for example, for strict convexity or convexity, compares f to the linear approximation of itself, right? Does everyone see this? And stop taking notes for a minute and just pay attention to me, because otherwise this might be confusing. But does everyone see that this is a linear approximation? Now what we want to try and do is we want to compare f to its second order approximation, it's quadratic approximation. And I want to say that not only is f bigger than its linear approximation, but it's also bigger than the quadratic approximation. Okay? And you'll say, but wait. And I hope you're saying this. This quadratic approximation here has this Hessian, and you have a, like quadratic form that looks slightly different from this, right? This is not exactly the same. So what's going on here? So here, this term, I can rewrite this term instead as y minus x 1/2. Can you see the green? Mu, 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 y minus x. Okay? This is exactly equal to this, right? Because I can just pull this mu out, and then this identity times y minus x becomes y minus x, and this just becomes the norm of y minus x squared. So this term is exactly equal to this. This is exactly in this format, okay? So now if f of y is approximately this, basically what we're saying is that we want to have the Hessian be greater than or equal to mu times the identity matrix. Do you see this comparison of what's happening here? I'm going to pause and take a question. Yes?
What does it mean for a matrix to be greater than?
For a matrix to be greater than or equal to another matrix, it just means that their difference is then positive semi-definite or positive definite. So if I have A greater than or equal to B, this means A minus B is greater or equal to 0. Good question. Yes, question? Does mu have to be positive? Yes, mu has to be positive. Thank you. Yes? Why are we replacing the Hessian with the identity times nu? So what our goal is our goal is to say if I have some function, maybe I'll draw it here. Let's say I have, these are my axes, and I have some function, right? Like this. What I want to say, I'm going to draw a cartoon. I want to be able to find some quadratic lower bound, okay? And so what I'm saying is that this thing is a quadratic function. If I can find a quadratic function that is always below my function value, then I'm good. This is basically saying the Taylor approximation is the quadratic that is, in a sense, closest to your function. But this is a local thing. You want to evaluate it at every single point. The Hessian value will differ at every point. By replacing this Hessian with this one identity times mu, I'm basically lower bounding the Hessian at all points in the domain, which allows me to get one quadratic everywhere, right? So there might be places where the Hessian is larger, the Hessian is smaller, but if you look at the smallest value of that Hessian, then you're okay. Does everyone see that? Kind of? That's a good question. Someone else? If not, I'll come back to you. Other questions? Yes?
When you say smallest, is like the smallest eigenvalue?
Yes, we will be concerned with the smallest eigenvalue and the smallest singular value. We won't go into this too much. Like, you can talk a lot about strong convexity. But in general, we will want to consider singular values, eigenvalues. I want to avoid going into it in too much detail because that really is the topic of a course like 227C. Here I just want to give you a flavor for what is going to come in that course should you choose to take it, and give you a very minimal perspective. Yes?
Are we considering real values of mu?
We're considering only real values of mu, yes. Yes.
I was thinking like integers or residual values.
No, real numbers for sure, yes. Definitely not complex, but yes.
So this need not be true for all mu. You just need to find the largest mu such that this will.
Yeah, you can just need to find the largest mu or some mu. Strong convexity is a property that ends up being very useful for proofs, as we are going to see later, and it's going to be useful for us in proving the convergence of gradient descent. So to prove that an algorithm like gradient descent converges, we will make assumptions on the function, such as the function being mu strongly convex. We're going to also talk about a smoothness characterization, which will come later. And basically, what strong convexity is saying is this kind of like a quadratic? Could you just pretend this was a quadratic and make life happy? Like, if you have not realized this by now, you will realize this very soon, is that our favorite as bestest functions in the world are linear functions. But if you really cannot have a linear function, then what do you want? You want a quadratic, right? And so much of life is about trying to make your function look like a linear function or like a quadratic function. And this is basically what we're building out a theory on. And then you keep doing kind of more and more cases to say, well, it might not be a quadratic everywhere, but maybe it'll be a quadratic in this part and this other part, and kind of piecing together these kinds of analyses. And there's a lot of theory that you can build on in general in optimization in this. We're going to do one of the simplest cases in lecture today. Okay? These are all excellent questions. Okay. So in general, we can say that this is satisfied whatever, never mind actually, let's not even bother with it. So I don't want you to worry too much about strong convexity. We're going to introduce it, but this is not going to be a kind of big part of the course. I want you to understand it as a tool, but we're not going to ask you some tiny little tricky corner question about strong convexity, okay? Strict convexity, we expect you to kind of know and understand. There's a bunch of examples on the homework. Strong convexity you'll talk a little bit about in discussion, but we're not going to ask you a tricky, complicated question on strong convexity. Again, this is really the topic of 227C. What we're doing here is an introduction. Okay, so don't stress about it. That's my kind of main thing. Okay, I'll keep this here and use the other board. Any last questions before I move on? Okay, now that we have these definitions out of the way, we can get to some of the exciting part of the lecture, which is gradient descent. Okay? So we have talked now for a long time about different kinds of optimization functions. And probably the optimization problem that we've talked about the most is least squares, right? So I have f of x equal to, in general, ax minus b whole squared. And I want to find that x that minimizes this. And this is an unconstrained optimization problem, right? There's no restrictions on the domain. We can kind of go anywhere we like. This is in contrast to, for example, something like the min-norm problem, right? Where we're trying to minimize the norm subject to a constraint. So you minimize x squared, norm of x squared, subject to the constraint that ax is equal to b. Do you see this kind of difference? Gradient descent primarily is a technique that we can use for such unconstrained, S-T-R-A-I-N-E, unconstrained optimization problems. So in general, a problem of the following, where I have some p star is the min of, let's say, some f naught of x, and let's say over all x belonging to Rn, right? And I want to find this p star, and maybe I also want to find the argmin, so I want p star is equal to f of some x star. Okay, I want to find p star and x star. And by unconstrained, I mean that my search space is all of Rn. I don't really have any constraints. I'm not saying that you can only look in this hyperplane or something like that. What gradient descent is fundamentally is it's a very sophisticated way for guess and get better. So it's saying start somewhere and then, you know, maybe try going in some direction. And maybe you'll try going in some intelligent direction, okay? So it's kind of the same thing as like when we say, you know, if you're stuck on a homework problem, you're stuck on an exam problem, like write something down. Don't try to figure out the exact optimum thing in your head before putting pen to paper. Just start somewhere, write something down, write down what's given, and then hopefully you'll make a step in some good direction, right? This is exactly gradient descent. Except we're going to do some math to prove and figure out what is that good direction. So in general, it's saying that let's say I want to find some minimum value for some f, right? In general, it would be lovely if all of my problems were like least squares, where I have an explicit formula, right? But least squares is one problem, and there's many other optimization problems for which we do not have an explicit formula. And so this is particularly useful when you do not have explicit solutions. Excuse me. So to start out with, let's say, you know, I was at some f of x. And maybe I was at f of x and, you know, someone told me what the value of f of x is. And maybe I had some kind of little friend or helper or TA who was nudging me along in the right direction. And from f of x, I wanted to say, well, instead of considering f of x, if you wanted to be close to the minimum, consider maybe f of x plus delta x, right? The million-dollar question is, of course, which delta x, right? Which delta x do I want to choose to get closer to the optimum solution? And this is what we're going to try and kind of figure out in a bit of a principled way. So if I have this f of x plus delta x, I can again write this out using my Taylor series, my first order expansion, right? And I can write this as f of x plus f of x transpose times delta x plus dot, 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 okay? So to think about which way, basically this is what this is telling me is that it's telling me which way am I going to move if I move from x to delta x. If I move from evaluating my function at x to evaluating it at x plus delta x, this expansion is telling me how my function value is going to move, right? And let's say we were to, you know, only consider the first order approximation. And to make this more explicit, let's say I separate out kind of the direction and a step size that I'm going to take. So if I write this as f of x times some step size s in some direction v, s is the step size, then I can write this as f of x plus again, the gradient of f of x transpose, here's an s, times this direction v. Okay? So I want to have something that is going to decrease my function, right? I'm thinking about, let's say, a function that I want to minimize. So how can I figure out which directions v are going to allow me to decrease my function value? What I have here is essentially just this inner product of this gradient of f of x and this direction v, right? So do I want the inner product between f of x and v to be positive or negative if I wanted to decrease my function value? Negative, right? I'm sorry? If s is positive. So let's just assume that s is positive. Good. Thank you. So in general, what would be the direction that I could choose that would maximize this value? Negative gradient of f, right? And why is that true? What do I know about this inner product? What's the inequality? Right, so Cauchy-Schwarz tells us exactly this inner product, right? And we know that if we wanted to maximize this, you would choose v to be exactly aligned to the gradient, right? You can, maximum magnitude is v aligned to gradient. But I don't want to align my v to gradient. I don't want to increase my function value. I want to decrease it. So to minimize this, basically I want to choose can you still see if this, I write this? Maybe I'll just do this here. Keep this up. This is not so important. Let me erase this. So I know that the gradient of f of x, inner product v, is always less than or equal to the norm. The gradient of f of x and the norm of v, 2 norm. This is Cauchy-Schwarz. So to minimize the inner product, I choose v to be equal to the negative of the gradient. Okay? So this maximizes the magnitude, right? So if I have a vector that's pointing this way, to maximize the inner point, I want a product in this way. But if I want to have a negative inner product, I want to point exactly the opposite way, right? So that my cosine theta is going to be -1 instead of +1. Yes, and then yes.
Is the magnitude v here something that we can use?
Great question. Hold on to that question.
Oh, I was just going to say maybe we should put a constraint on the magnitude like the units.
Great question. So this is a question that always comes up. And you know, when we talk about Cauchy-Schwarz, often when we're doing Cauchy-Schwarz, we have some kind of constraint on the vector. We're thinking about a norm 1 vector, right? For example, all of those, the very first lecture, we did an optimization of our norm ball, right? And we thought about the different norms, like we thought about the 2 norm and the p norm and the infinity norm and things like that. Here, we don't have any such constraint. And in fact, we're not going to explicitly put it's important that we don't put a constraint. And you'll see why in a couple of minutes, maybe 15 minutes. But what we want is we want to be able to move according to what the gradient tells us. In particular, for example, for a convex, for in general any function, what do we know about the gradient at an optimum point, right? At the minimum, what is going to be the value of the gradient? 0, right? In an unconstrained optimization problem, which is what we're thinking about. So by not normalizing v, and by saying that v is actually exactly the gradient, it basically says that when you're close to the gradient, when you're close to the optimum, don't move too much. If you're far away from the optimum and your gradient is large, move a lot. This is because close to the optimum point, your gradient is also small. Okay? So there's a natural element of convergence that is kind of built into the algorithm because of the way it's formulated. So we're explicitly not normalizing out the v. This is a very good question. Is everyone with me? Yeah? Yes?
I'm curious about why we're using the Taylor approximation on the right as an exact equality.
Good question. We're definitely not using it as an exact equality. We're just using it as an approximation. And really, why I'm using this Taylor approximation is as a motivation for why you would want to do that, right? When you're stuck on a problem and a TA gives you a hint to move in the right direction, why is this hint, why is moving in the direction of the gradient a reasonable thing to do? It's a reasonable thing to do because of this Taylor expansion. This does not prove that this will take you to the optimum. It does not prove convergence. All of that is extra work that we have to do later. But this is giving us the intuition for why this might even be a reasonable idea. Does that make sense? Yes?
Couldn't this, if our gradient was, really steep,
Uh-huh.
couldn't, a step take us farther away from our rhythm?
The question is, if your gradient is too large, could you have a bad situation? Absolutely. This is what the rest of the lecture is about. So hopefully by the end of the lecture, that question will be answered. Okay, so we're getting questions that are moving us forward, so let's continue to move forward. So nominally, the gradient descent algorithm is written in the following way. It says at time k plus 1, I want to evolve from xk as minus eta times the gradient of f at xk. So this step size parameter that I called s is often called eta in the optimization literature. And this is just the direction of the gradient. Note that this is about how x is changing. This is not how f of x is changing. I get a lot of questions in office hours where students are confused between whether this equation is for f or whether it's for x. Okay, so this is the argument of the function. This is where you're evaluating the function. Okay? And it's saying that if I'm at xk, if you want to nudge in the right direction, consider moving by some amount eta in the direction given by the gradient, okay? X naught is what we're going to call our initial point. And eta, I'll just write this, is our step size, okay? And, now you could have some wonderful, algorithm that says, oh, you're at x naught. Okay, move here, move here, move here, move here, move here, move here, move here. It could take you somewhere totally random, right? How do you know that this is going in some good direction What does that even mean? And so to understand whether gradient descent is a good idea or not, we need to prove something like convergence. And what does this mean? This means that eventually, as you take many, many, many steps, you are getting closer and closer to the optimum. Or basically, you get x1, x2. Eventually, you get to this appropriate x star, which is your optimum point, right? Yes?
But the x star should be like a local minimum, correct?
So the question is, can x star be a local minimum? Absolutely, x star can be a local minimum. In the case of a convex function, you will get to the global minimum. If you don't know anything about convexity, you could very well end up in the local minimum. All we're saying is that we'll get to a point where your gradient is 0. Okay? And we will prove that you can get to the global minimum in the case of convex functions. Yes?
How can we ever reach the global minimum in a finite amount of steps?
We'll do some examples, but you can definitely do it. And the key here is that, let's say, somehow, by some hook or crook, xk is equal to x star. Okay? You manage to somehow at the kth time step come to x star. Then what is xk plus 1? Well, it's x star minus eta times the gradient at x star. But what is the gradient at x star if x star is indeed an optimum point? 0. So minus 0. So basically, once you arrive at the optimum, the nice thing about gradient descent is that you never move, because your gradient is now 0. Okay? So let's do this in the case of an example. And we're going to do our favorite example, which is, everyone has to know the answer to this by now. So we're going to consider f of x is equal to norm squared ax minus b. It's remarkable how much deep theory you can understand by working out the most fundamental example. It never ceases to amaze me, actually. But what we're going to do is we're going to say, say we start somewhere, and we're going to evolve to see if we can actually converge. You would ask, well, why do I care about gradient descent for a problem like least squares, where I already have a formula? I've had a formula for the past 3 years since I was a freshman, right? Or so many years. Like, who cares about one more way to solve gradient descent? Turns out, to solve least squares, turns out that this is actually quite useful. And we'll see why, but I'll show you in a minute. So let's just compute what is the gradient of this. You've already done this many times. So let's say that this gradient is 2A transpose times AX minus B, right? This is the gradient of f of x. And so now if I was to take the direct solution, so the direct solution to least squares is A transpose A inverse A transpose B, right? And let's say we're dealing with n by n vectors. So let's say A transpose A is an n by n matrix. What is the kind of order of computations that I need to do to compute this least squares solution? O of n cubed, right? A matrix inverse, computing a matrix inverse is n cubed computations. Okay? We haven't shown this in this class, but just accept it as a fact from me for now. taking a matrix inverse is approximately n cubed. Computing this gradient, what is the order of operations here? This is an n by n matrix, and this is just a vector. So there's n squared order of operation here, right? So now, let's say I had to take gradient descent. So every gradient descent step is O of n squared, right? You know, let's say my n was 1,000,000. If I can get gradient descent to converge in maybe 10 or 12 steps, which you will see in an example that you can, you're saving a tremendous amount of computation. You're actually an order of magnitude cheaper to do gradient descent than you are to actually compute the explicit solution. Okay? So for many large problems, even if it's a least squares problem, even when you could explicitly calculate the formula, you will often end up using an algorithm like gradient descent. Yes, question?
But don't we have to do step size amount of n squared computation?
So it depends on how many steps you take, right? So if you take, you know, whatever, 10 steps, then you have to do 10 times O of n squared. And that will depend on the step size, and we will talk about how to choose the right step size. We haven't gotten there yet, but so if you have a bad step size, it's definitely a bad situation. Yes?
But, excuse me, for the least squares, you don't need to explicitly find the inverse. You just need to solve AX's including its own squares.
Great point. So the point is that, well, you don't always have to do O of n cubed operations. There's lots of ways to do least squares faster. And that is true. For example, you could use QR decomposition to speed up, like you did in the homework problem. So it depends on the instance. But often in practice, what people do is that they will do gradient descent. So it's definitely true that you could speed this up. For a general case, this is often the easy and quick solution to do. These are good questions. And again, if you had a straight least squares example, you might not do gradient descent, right? The reason we're going to do it out for least squares is pedagogical, because I want you to understand how gradient descent is behaving, and it helps you see kind of where things are getting stuck, where they're not getting stuck. It's more of an illustrative example to see the power of the algorithm, and then you will apply it in various complex situations. Is that okay? Great. Okay. So now, let's actually do this out. So let's say, what is my gradient step? So I'm going to say xk plus 1 is equal to xk minus eta times gradient of f at x of k, okay? And I can just plug this in. So this is xk minus eta times, so I have 2 times A transpose times A xk minus B. Okay? I can rearrange and kind of swap these things around, and I can write this as identity minus 2 eta A transpose A times xk minus 2 eta A transpose B. So I have this xk, I put them together. I replace this by an identity. So this is identity times xk minus 2 eta A transpose A. And then I pull all of the constant terms out together here. So for those of you who took 16b, I know that you've seen this. I know some of you haven't taken 16b. But let's say I had some system, let's call it zk plus 1, it's just a scalar, times A times zk plus some constant, let me call this C. Okay? Let's say A is equal to 0.5. What is the limit of zk? Okay, let's forget the C for now. What is the limit k tends to infinity of zk? What is this going to converge to? 0, right? Great. If I had some constant here, it's a little bit more involved to figure out what it converges to, but is this thing going to blow up? Is it going to go to infinity, or is it going to be bounded? This is going to be bounded, right? Okay. What if A was equal to 2 instead? Is this thing going to blow up to infinity, or is it going to be bounded? It's going to blow up, right? What if A was exactly equal to 1? It's unclear what's going to happen, right? Like, depends on whether the C exists or doesn't exist. A is equal to 1 is complicated. But in general, if A is strictly greater than 1 and positive, what can you say? It's always going to blow up, right? And if A is strictly less than 1, between 0 and 1, let's say, it's always going to stay bounded, right? Because you're always decaying things. So this is what happens in the case of scalars. What does this equation over here look like? It's an equation of this form, right? Except now, instead of scalars, what do we have? Matrices, right? So what we care about here is the eigenvalues of this thing. In particular, we're very lucky. What kind of matrix is this? Symmetric, right? I is symmetric. A transpose A is symmetric. So this difference is symmetric. So I know that the spectral theorem is going to hold here, right? And so because the spectral theorem holds, I know I can do an eigendecomposition, and I can write this power, this this matrix to some high power. I can write it in terms of its eigenvalues, right? Everyone remember that from diagonalization from linear algebra? Okay, good. So keep this in mind, and now we're going to actually prove that this works. So to show that basically I'm going to converge, right? I want to show that this converges to the right solution. And in the case of least squares, I actually know exactly what the right solution is, right? I have a formula for it. So I know that my solution is A transpose A inverse A transpose B. And to show basically that I'm getting closer and closer to this solution, I'm going to want to look at the distance xk plus 1 minus x star, right? If this is my x star, I want to look at this difference, right? There's many different ways of proving convergence. This is one way of proving convergence. Okay? So I'm going to consider xk plus 1 minus A transpose A inverse A transpose B. And I can write it as this thing minus A transpose A inverse A transpose B. We're good? Okay. Now I want to do something. I want to be able to kind of merge these things together and make something kind of, I want to prove some convergence, right? So I want to be able to basically get something times, it would be nice if I could get xk minus this times this thing out, or something like this, right? Yeah?
Should there be a plus instead of minus before the 2 eta?
There should be. I think you're right. Yes. Thank you for checking that. Thank you. So what I'm going to do is I'm going to write this. I'm going to copy this. I'm going to write this as plus 2 eta times A transpose A times A transpose A inverse A transpose B minus A transpose A inverse A transpose B. I just kind of inserted this stuff in here. Okay? But now I'm kind of in a nice situation, right? This I can write as this thing plus, can I pull out this quantity? My x star, essentially. Right? Both of these things are the same, so I can write this as 2 eta A transpose A plus identity times A transpose A inverse A transpose B. And so let me make sure my signs are correct. So this times this should give me a plus sign. This times this should give me a minus sign. So I want to have a minus here and a plus here. Everyone with me? Now, is there a nice way I can pull this all together? This term is basically this term, right? So I can write this as I minus 2 eta A transpose A times xk minus A transpose A inverse A transpose B. So x minus x star in one step, whatever my distance is from my optimum, I have related it to what my distance was to my optimum at my previous time step. Does everyone see this? Everyone see why this is helping us understand where gradient descent is moving? And so it's telling us basically that this matrix dictates how your system is going to move and evolve, right? And now if you wanted this to converge, remember this is a symmetric matrix. So if I have some symmetric matrix S, I can write S as U lambda U transpose, and S to the K is equal to U lambda to the K U transpose, right? If you don't remember why this is true, go look this up. Definitely need this on the exam. But now, what condition do I want to have on my symmetric matrix to have this converge? What do I need to be true for all of this? Positive definite could be, well, greater than 0, less than 0. What if all of the eigenvalues of this matrix were 2? Would that be a good thing? No. What if they were all 0.999999? That would be okay, right? What would happen as you took powers? Are you going to converge? Are you going to get closer and closer? Like, you want this to be strictly smaller than this, right? At every step, if my optimum is that table, I want every step to get me closer to the optimum, not further away. So I want this to have eigenvalues that are strictly less than 1. Okay? Doing this proof out explicitly requires you to kind of think through what is happening here. It's on the homework. I'm not going to do out every step, but I want you to see what's going on.
We also want our eigenvalues to be greater than negative 1, right?
You want the absolute values of your eigenvalues in general to be smaller than 1. So basically anything that is less than 1 in magnitude will converge to 0, right? Similar, just like here, if a was negative 0.5, would you be fine? Yes?
So the best rate of convergence we can achieve using this method is like super linear?
So this gradient descent in this case has exponential convergence. So you're converging exponentially fast, and your rate is basically given by the eigenvalues of this matrix. Yes?
How can you apply this? Like, maybe I'm understanding that, but can you only apply this process because you knew this solution?
Great question. He's like, suspect, right? I love it. You're like, yeah, you're talking about gradient descent, but least squares, you know the solution. What other problem do you know the solution for? Basically, nothing. And yes, so we have not proved that gradient descent converges for everything. All we have shown is that here, when the eigenvalues of this thing are less than 1, so if, no, I should write over here, right? You prefer this to be here, and I should write over there? So if evals of, or absolute value evals, so like basically absolute value of the eigenvalues of I minus 2 eta A transpose A are strictly less than 1, then gradient descent converges for least squares. This is one very, very special function. It's the nicest function in the world. This does not prove anything for any other function. That is what we're going to do next. But that proof basically follows this general strategy. And before going into something that has mu strongly convex and L smoothness and notation and notation and notation, it's always nicer to understand something in the simplest case where you feel confident, okay? But this general strategy will be useful. Like, what I want you to understand is this general strategy, okay? And in general, I mean, so, this is one way of proving convergence. You could also prove convergence more directly by, for example, computing a particular value of a function, right? So, you're saying that here I'm looking at the difference from the optimum, and that's a way of converging. Other ways of proving convergence also exist, right? So this is just one example of how to prove convergence. So what I'll do is I'll give you a little bit of a preview of what's going to come next, right? So this demo will show you a little bit about how gradient descent behaves, but since we cannot do that right now, I'll build on Rohan's question, right? Which is that why, we did this for least squares, but so what? What next? And here, what we're going to show is that for certain kinds of functions, in particular, for, let's say I have some function, and it's a convex function, let's say. Well, this is not a convex function, so let me draw a convex function. Right? Maybe it's differentiable, maybe it's not differentiable. But now, if I know that this convex function is mu strongly convex. So remember, what does mu strongly convex means? It means it kind of fits in a bowl, right? And that bowl has Hessian mu times identity, right? So this is what this mu strongly convex means. And it's one way of saying that this function is kind of like a quadratic, okay? And it's saying that basically your gradients for this function are at least changing kind of somewhat. They're not super static. They're not, you're not going to get stuck somewhere. You don't have zero gradients or very small gradients showing up too fast. Because what do you want to show? You want to be able to show that in some reasonable amount of time, you're going to converge to the optimum point, right? I made an argument for you for why you might want to use gradient descent for a problem like least squares. But if it takes you 10 bajillion steps to get there, that's not a particularly useful algorithm, right? You want to basically show that you get there in, like, before your computer crashes, for example. So that's the question, like how fast can you get there? And so what we're going to show is that for functions that are both mu strongly convex and what we will define as L smooth, you can have exponential convergence. And what I mean by L smooth is that not only, like, L smoothness is basically that you can fit a cup inside your function. So this mu strongly convex says that you can fit inside a bowl. This says that there's another quadratic that can upper bound your function, okay? And what that is saying is that basically your gradients are not changing too fast. So somehow if you had something that was very, very sharp, what you will see, and if we had been able to do that demo, you would see it, and you'll see it in the next lecture. If your gradients are too wild, and some of the questions have come in this direction, you could kind of, you might have, like, let's say I'm here, and my gradient bounces me completely all over my domain, right? I could have very steep gradients, and that would be terrible. I'd never converge, okay? So this is a way of saying that your gradients are basically not changing too fast. And this is a way of saying that they're at least changing a little bit. Because if you're like, my gradient keeps me here, 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 I'd never get anywhere, right? If I have tiny, 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 I keep moving very, very locally. So if I have both of these things, which are true for quadratics, and basically if an upper and lower bound my function by these quadratics, then even if my function is not a quadratic itself, I can have many of the nice properties that exist for least squares, and I can show that basically this will also have exponential convergence. So we'll get to that in the next lecture, hopefully with a working computer. Thank you.